welcome back for another round of exploration systems engineering, biological materials, optical, and electrical. Quite a bit of fun. So, for those of you that weren't here last time, just as a really quick reminder, I will be your moderator. At 3 minutes remaining, I'm going to hold this sign. It says 3 minutes. At 1 minute remaining, I'm going to hold this sign. It says stop. That means you have a little time to wrap things up. After 1 minute is up, to make sure everybody gets enough time because we're moving so fast, I will give a lovely round of applause, and you will be Broadway music off the stage. With that, we're very excited to introduce our first speaker, Juan Machado from the University of Arizona.
Good afternoon, everyone. I hope you guys are all full from lunch, nice and stuffed. And once again, I'm Juan Machado Jr., and I'm a mechanical engineering student at the University of Arizona. And my mentor is Dr. Hannah Butenoff. And first, I would like to give thanks to the University of Arizona, NASA, and Space Grant. And let's get into it. So this is going to be the comparison of in-process desorption for metal additive manufacturing using simulations. So first, let's go over what additive manufacturing is. It's taking a 3D model and slicing it layer by layer to bring a digital part into the physical world. And there's many types of additive manufacturing. For example, there's material extrusion, which is your typical 3D printer. You can make a range of geometries with that. And what we're going to be talking about today is laser powder bed fusion and direct energy deposit. And then we have traditional methods of manufacturing, for example, machining. And an example of machining is subtractive manufacturing. You take a block of material and you take it off little by little of the material until you get your part out. And from this, it's pretty wasteful, it's time consuming, but you get a quality part that's strong and able to withstand forces. With AM, additive manufacturing, you have rapid prototyping, it's more material efficient, and this is important to aerospace companies like NASA to create a lower flight to buy ratio so we can spend less money to get more missions up to space. And it's also important for other companies to save money. But the thing with additive manufacturing, these parts don't have the same quality as regular machine parts. And that's the problem we're going to be talking about. So thermal history determines the quality of the part, which includes the microstructure, deformation, and residual stress. And thermal history varies between parts and these methods of additive manufacturing. So we want to quantify the differences in between DED and laser powder bed fusion for a range of parts to look for which process would have the best quality. And we can see on the top right here, this is direct energy deposit. It's shooting out metal powder, and there's a laser beam hitting the powder, and it creates a layer. And then at the bottom, we have laser powder bed fusion. So it rolls over a layer of powder, it shoots the laser down, it moves down, rolls over another layer of powder, shoots a laser, and the process is repeated over and over again. All right, for methods, we use fine element simulations. For laser powder bed fusion, we used ANSYS additive. For direct energy deposit, we use ANSYS workbench. And we're taking measurements of the max displacement and max stress. We use the same material, which is titanium 64. We use similar but not the same parameters. And the parts were created by a previous spacecraft intern, Pablo, for his research project about laser powder bed fusion. So I used a total of 21 parts. 4 of them are revolved parts, so you take a shape and you revolve it around the axis, and then 3 of them are extruded parts. So first right here, we have extruded parts. On the left-hand side, we have laser powder bed fusion. On the right-hand side, we have direct energy deposit. And you can see where those highlighted red areas is where it's gonna have the most deformation, and you can see it on both sides. Next, we have the max stress, Once again, on the left-hand side, we have laser powder bed fusion. Right-hand side, we have direct energy deposit. And this is a bar graph of this information. On the left, we have the deformation. On the right, we have the stresses. And we can see in this extruded part that for the most part, deformation is a lot higher in laser powder bed fusion. And then in the stresses, direct energy deposit has a general less tendency to have max stresses. And then this is one of the revolve parts. On the left-hand side, once again, we have laser powder bed fusion. Most of the deformation is going to be in the center. For direct energy deposit, we have most deformation at the top of the part. Now we have the max stresses once again. And the max stresses are going to be in the center, kind of weird looking lines. And then for the direct energy deposit, we have the stresses mostly being at the bottom of the part. And here's the data for those ones. For the revolve parts, we can see that deformation is a lot higher for some reason than laser powder bed fusion. But depending on the geometry for the stresses, it might be higher for, say, this part right here, but then some of them are going to be lower. And then for the rest of the parts, we don't have time to show them all, so I have the graph right here showing the extruded. We can see on the top, we have the stresses. And like again, for the most part, direct energy deposit has less stress. And then for the deformation, depends on the geometry, but most of the time, laser powder bed fusion is going to have a higher deformation. And then these are the revolve parts. Top, we have the stresses. Once again, it seems that direct energy deposit has less stress on the parts. And deformation, DED has more deformation for most parts than laser powder bed fusion. And as you can see, I have a little GIF right here. Sadly, I couldn't put the whole animation of it being built from top to bottom, but you can see it a little bit being built because I don't know why, but showing the whole animation was like half a gigabyte and I couldn't fit it in. So conclusion is that we have the extruded parts for laser powder bed fusion had more deformation and more stresses. For the most part, like I said, it depends on the geometry. And then for the revolve parts, we're going to have more deformation in the direct energy deposit, and the max stress is going to be dependent on the part. All right, I want to say thank you to everybody. Thank you for listening. And once again, thank you to the U of A, UA Space Grant, and NASA. And then I have a video that's going to be posted soon to my professor's website, so check out the Manufacturing and Design Exploration Lab on how I set up the whole simulation. Thank you.
Time for a few questions.
Yes.
Similar to how in subtractive manufacturing you can move an incomplete part to a different type of machine to do different type of work on it, can you combine powder bed fusion and direct energy deposits to kind of find a good intersection between not a lot of deflection and not a lot of stress, or does it have to be one whole process?
I'm pretty sure it has to be one whole process because when you're printing a part, it expands and shrinks. When it heats up, it expands. When it cools down, it shrinks. So if you let enough time for it to cool down, it's just going to cause more distortion. Yes.
Do you know why there was a difference between the deformation in the revolve versus the extruded ones? Like that it was opposite types?
No, we don't have any conclusions about that yet. It's still in preliminary trials, so we need to make sure that our data is going to be accurate. And like I said, these are all simulations, so we haven't actually printed the part. Yes.
Was it in that software that you mentioned earlier that you did the stress analysis and the deformation analysis?
Yes, for both of them, you're able to look at the deformation and stress with ANSYS additive. With ANSYS Workbench, there's a ton more options. You can look at so much stuff on there. And one thing I didn't know is simulations take time. They take so much time, which is surprising. All right, thank you.
We'll hear from Todd from Arizona State University.
Hello, my name is Mitchell Todd. I'm a mechanical engineering student from Arizona State University. And during this project, my mentor was Dr. Anup Grewal. He's a professor at Arizona State University. Is there a remote? Oh, sorry. Okay, so as a brief introduction, the project we're tackling today is essentially robotic arms are a big area of space exploration because they allow for manipulation in places where humans cannot go. So right now, an example of a robotic arm being used is called Canadarm on the space shuttle. It's not in service anymore, but it's just an example of why we need to focus on robotic arms. But right now, coding for these arms is very extensive because they use a process called inverse kinematics. And especially as you get more linkages in your arm, to calculate these inverse kinematic results, it becomes very demanding and time consuming. So essentially with this project, we're trying to see if this can be completely streamlined by using neural networks to create a mapping between the solution and the position. All right, so before starting, we did a little bit of research just to see what was kind of out there already. We found a couple papers here. I won't go too in-depth in them, but there's different methods that people are using with neural networks to tackle this project. For example, you have joint space segmentation, and that's pretty much just saying that neural networks aren't always the most accurate. So by limiting the Cartesian space that an arm can move in into several segments, you can increase the accuracy. So then we just saw more methods like that, but then we decided to see what we could do. Okay, so before actually doing the inverse kinematics, we needed a way to find the desired position value. And so that was just a simple vision neural network using a convolutional neural network called YOLO V2. That stands for You Only Look Once. It's one of the more popular image recognition neural networks out there right now. It essentially divides the image into a grid, and then the neural network looks over each image individually and decides which square of the grid has the highest probability of containing the object you want to find. All right, so there's a lot of different neural network architectures you can use. One of the most common is called feed-forward neural networks. These are like pretty much as basic as it gets when it comes to neural networks. They're only a couple layers, which means they run really quickly, and they don't require that much training. There's also some different ones that kind of stem off of feed-forward, like for example, function fitting and fuzzy logic. Fuzzy logic is a little bit special because it uses a different area of mathematics called fuzzy logic, which pretty much doesn't give you an exact answer. It instead gives you probabilities and chances that something that might happen. But for this project, we decided to use feed-forward just to keep things simple. All right, so initially we trained a network and we put it to test, and we saw very low accuracy, and we concluded that this was because inverse kinematics, the way it works is you have an arm and there's a desired position, but there's multiple ways to reach that position, so it's a nonlinear function, and because of that, the neural network cannot determine which one is the best one, so it gets a little bit confused and you get low accuracy. So then we decided to experiment with some different methods to kind of help the network through this. And the most successful result was training individual networks for the X and Y coordinates of the network, so that way we just found it had the best accuracy by dividing, pretty much giving multiple networks for each position. So this is kind of to show what I'm talking about. If you imagine a two-linkage arm, kind of like an arm, you can move at this joint right here, and you can move at this joint right here. And so this kind of maps out all the possible locations you can move just with 2 degrees of freedom. And then so once we tried to replicate this with our neural networks, we got our error graphs over here. And you can see blue is less error, which means it's a good thing. And you can see how kind of towards the edges, it starts to replicate the possible positions. So that was a good sign because it told us that our network was accurately replicating the possible positions. And then here's a quick little simulation just showing if you draw a random curve, the arm will try to replicate it. It's kind of hard to see, it's a faint line. but that's a simulation of a robotic arm following the desired path without any mathematics, just neural networks. So to implement this in real life, we played around with a pretty simple 2 degree of freedom arm. And then we hooked it up to an Arduino Uno. And we pretty much just tested it in real life, and it worked quite well, quite surprisingly. Yeah, and future, we want to optimize this process by making it even more accurate. So yeah, kind of adding on to that, even though we achieved kind of good results, there's still a lot of accuracy that can be improved. So we're thinking about taking the idea of having multiple neural networks even further by implementing this more to see if it increases the accuracy. We're also experimenting with combining multiple methods that you saw in the research earlier towards our own method to see if when they're combined we can get more accuracy. Yes, that's kind of what that says there. And then also with the computer vision, that was one area where we couldn't really figure it out, because when you combine the computer vision with the inverse kinematic neural network, you kind of get a little bit of disconnect. And so we're trying to research how we can make that even more streamlined. Yeah.
So in your problem, do you have situations where you have two different values of the angle that give the same final location? And if you have this kind of ambiguous situation, what do you do?
Exactly. So that's what we're trying to solve. Essentially, by dividing it into multiple neural networks, then there's only really one possible solution. So that kind of eliminates it, which is why we chose this method.
When you're doing this, the deep learning that you're engaging in here, have you considered running like manual trials or human-based trials as well to measure against
Oh, you mean like for the training data?
for the training data?
Yeah, so we thought about that initially, like having an actual camera record the possible positions and then use that towards our training data. But the thing is, it just is a very extensive process to extract all they're called bounding boxes, and it's what you use for the training data. And so that's a very lengthy process, so we decided to do it in simulation.
Well, I was thinking less like that and actually more, so there's a problem in robotics called the problem, the fallacy of perfection, which means a lot of robotics engineers, when they're doing inverse kinematics, try to aim to make the robot perfectly perform an action, but humans only perform an action perfectly about 75% of the time. So your goalposts might be lowered for you a little bit if you do some UX testing first. Measure it against human, drawing that shape as well to see how close you have to get before you're not at
Before
yield.
it works, yeah. I like that.
I know it's released, just released YOLO-V8, is there any like consideration to move up on YOLOs or no network?
YOLO V8 is like obviously a lot better than YOLO V2. But just since the focus of this project was primarily inverse kinematics, we decided to keep it simple for the YOLO part. But certainly in future work, we would probably experiment using newer versions.
Yes, what kind of challenges do you expect when you move to the 3 degree of freedom robot with neural networks?
So when you have a 3rd degree of freedom, you have depth that you have to worry about because the arm can be further or closer. And so when you're using computer vision, you have to consider the size of the position because that'll tell you how far away it is. And so that would require an additional neural network that can interpret how far something is from the camera.
Is the neural network the same as AI?
So the stuff like ChatGPT and AI, stuff like that, essentially is much more complex versions of what we did. A neural network at the base is just a lot of linear algebra. Without going too much into it, there's a lot of matrices involved. And each time a matrix is recalculated, there's weights that update it and make the numbers closer to what the desired result is. So it runs through that hundreds of thousands of times, and then you kind of get your result. But essentially, ChatGPT is using the same thing, just on a much more advanced scale.
This is Michael Vietnam from University of Arizona.
Okay, so hello, my name is Michael Villasana. I'm a senior at the University of Arizona, majoring in electrical and computer engineering, and during this 2 semesters, I've been actually working with collaborations with the Department of Aerospace and Mechanical Engineering with, more specifically, Professor Jihan Tenga on smart sandbags for autonomous lunar construction. And so, as many of you may know, NASA's Artemis mission seeks to establish a permanent residence of humans on the moon to kind of serve as a stepping stone to go to Mars. And so, constructing a lunar infrastructure kind of presents a very significant challenge with limited resources and limited hand from human intervention because we are restricted to the resources. We started proposing autonomous systems that are crucial for this lunar construction that basically enable an eventual creation of a self-sustainable lunar base. And so the existing plans are that we actually do want to create a lunar base, but before we establish humans in this base, we need to make it autonomous and we need to make it sure that it could run by itself and everything could be made before we come in and start establishing our presence there. And so a vital structure is actually a super adobe, which is a proposed structure that would use what is known as smart sandbags, which I'll explain later what they are, to basically make these super adobes. And they will be made out of regolith from the moon because we are limited in resources and sending that payload to space is going to cost us a detrimental amount of money. And so these smart sandbags are part of an architecture that can help with maintenance, monitoring, and sensing of the lunar base in general. And so my research comes with the networks proposed to kind of create these infrastructures and basically establish this lunar base. And so my lab proposes that we use 2 kinds of networks, a distributed network and a centered network. So the distributed network, as you can see here, is more of a computing network, basically larger, and it's dispersed all around the lunar base. With this focus on just focusing on computations, kind of serving like a supercomputer for the base. However, the sensor network, which is a more smaller and concentrated network that pertains to monitoring singular sandbags, either 1 or 2, which are seen over here in the right diagram, kind of are singular devices that will monitor the health of the lunar base and transmit that information to a gateway, which could later, if you want to basically run a computation with data from these sensor nodes, send it to the computing network, and they could basically alleviate a task for the robots that will be helping with the construction. And so where my area comes into work is I created the sensor network, and I created an actual physical network of sensors and microcontrollers. And basically, it consists of individual sensors powered by smaller microcontrollers, and more specifically, I use the Arduino Nanos, where each microcontroller has capability of wireless transmission, just because we don't want everything in the Super Adobe to be physically wired. We want everything to be wirelessly transmitted to a gateway, which could connect to a distributed network, either via LAN or just wireless. And so, the bigger microcontroller, which is I use an ATmega. 2560, which is just an Arduino Mega, serves as a gateway to the distributed network just because it has larger registers and more capability on the bus. So the wireless transmission was actually achieved using a wireless transceiver, more specifically an NRF24L01+. The orientation was actually just determined with an MPU 6050, which is an accelerometer and a gyroscope. Localization was actually achieved using an ultra-wideband module, which is a DWM-1001C, which kind of gives us accuracy to the centimeter precision. The force sensing was achieved using a generic force-sensitive resistor. The proximity was actually used with a simple IR obstacle avoidance sensor, and some extra life support sensors that I included just for the fun of it. It was the temperature sensor, which was just using a DHT11 sensor. And on pictures, you guys could see some prototyping, and then when things started to finalize and started to be soldered together. So from the results, we were actually able to successfully transmit over wireless the orientation, the position, the temperature, proximity, and determine if a sandbag was sagging. So correct predictions that really help us with the actual construction of these super adobes. As you can see here, here's some graphs that like show the force sensitivity of these resistors and denoting when we have something that's falling or something that's not balanced, because this could be crucial to in the structural integrity of the actual super adobe. And on the right here, we just see the actual transmission to my computer from, I'm just reading it serially from a microcontroller to, from a smaller sensor to an actual, the gateway. Here's some more demos. This is me actually moving and simulating in MATLAB the actual moving of the localization of the DWM-1001C module. Basically, I'm just transmitting the coordinates and in real time processing it and showing it in MATLAB, and just as I move around with them, carrying them in my hand. And there are some future works that we want to move this to Unreal Engine just so we could get physics-based simulation. So, yeah. Here's some more pictures of the setup. Here on the left, we have some force-sensitive resistors attached to the sandbag. Ideally, this has to go inside, but we haven't made the actual encasing for it yet. So that's what we're currently doing. Here's the DWM-1001C modules and the gateway microcontroller. So in conclusion, we were actually able to localize positions of the sandbags within 20 centimeters of error. We were able to detect sagging of the sandbag for lunar reparations or construction. We were actually able to successfully wirelessly transmit from sensors to an external microcontroller that was our gateway. And we were able to visually simulate this in MATLAB VR. Yeah. I want to give a quick thanks to Space Grant, the consortium, as well as explain my gratitude to the Lunar Base team, my lab, and Dr. Thango for this opportunity. And I want to thank my grad mentor, Siva. He's not here, but I want to thank him, and just everyone that I work with in the Space Treks and Asteroids lab. Thank you.
A few questions. Is there an upper limit to how many of these transmitters you can have in a specific area? Or, because I think there's like a lot of sandbags, right?
Yes, those are supposed to be like at least like hundreds. There is a limit for a certain channel. However, we want to make a multi-layer network approach.
Okay.
So that way we could like just increase the number of sandbags that basically serve as the topology for this network.
Do you think once you put the casing in your sensors will affect your results?
So we have tested with some encasings. As far as we've tested, there hasn't been any loss of integrity with the data. However, we have only limited to what we could 3D print, which is just certain material.
How frequently are you sampling?
It all depends. It uses SPI. I think right now we're sending data because it's not too rapid with what's changing. I'm sending about every 10th of a second.
So, are you worried about radiation hardening? Like, do you have plans in mind to, like, MRAM and stuff for radiation hardening?
Yes, so that is to be considered. Because this was just a prototype, we just wanted to make sure it was feasible. Our actual next step is to actually encase this for radiation hardware.
Do you know what kind of pressure the case is going to be put under, let's say, when the sandbags on the bottom of the stack?
Oh, I can only imagine it's going to be immense pressure, yeah. But the intensity of the reason that we chose these force-sensitive resistors is that once they have stabilized, their intensity would be reached to a max, and it will just flat out there. And we know that it will be the structural integrity would be withheld.
Have a position from the machine.
Am I good to go? Oh. Okay, good. All right. Hello, everybody. My name is Samantha Beauchesne. I'm a geological science major at Arizona State University. I'd first like to start off with what brought me here to you all today. I have the pleasure of working for the NASA Psyche mission on the student collaboration team at Arizona State University. On this team, my role is communications. So mainly I do social media outreach. I post on all our social medias, basically just spreading the word of the mission, trying to bring awareness to the mission so people can learn more. I'd like to acknowledge my mentor who led me here today. She runs the student collaboration team. She led me to this research that I'm going to be discussing with you about imaging meteorites. The NASA Psyche mission led by ASU's Dr. Lindy Elkins-Tanton, launched October 13, 2023. The orbiter's mission target is the Psyche asteroid, which is the only known place in our solar system that can examine directly what may contain metal from the core of an early planetary building block. Sorry, I'm a little nervous. Through the Psyche Capstone program, a team from RIT designed a system to obtain high-quality, uniformly illuminating images of meteorite samples. My part of the Space Grant project was to recreate this process through the system updating the procedure and also troubleshooting the aspects of the design, including documenting and updating the manual. The images that will be obtained from this system will be added to a database, like you see on the screen. And through these images that we'll be obtaining will first be analyzed by humans and then by a machine learning algorithm. In order to accurately evaluate and characterize meteorites, scientists must first examine the composition of the meteorite samples. This is usually done through a visual inspection of the surface. Now, what brings a challenge to this is the presence of inclusions or minor minerals that may be enclosed in the larger iron meteorite samples. Many inclusions, when in iron meteorites, have a spectrally featureless nature, which poses a challenge for that accurate identification of its composition. In an effort to address these challenges, I introduced the System for Analyzing Meteorite Inclusions, or SAMI. SAMI was designed to provide a user-friendly, easily repeatable process. Think IKEA, but for a meteorite imaging system. SAMI provides that process to obtain images that will be high quality and uniformly illuminated. So you may be wondering what's next, what's now in our research. By the end of these 2 semesters, the final outcome is a rebuilt, fully functioning system that can acquire and obtain and store the images for a future computer science Psyche capstone team. Thank you. Are there any questions? No? Perfect.
Thank you very much. Leo Salazar, University of Arizona.
All right. Hello, everybody. My name is Leo. My full name is Lionel Manzar. Today I'm going to be presenting my project this year. I worked with an orthopedic surgeon, Dr. David Margolis, and we are studying implantable bone sensors for monitoring fracture healing. And I don't have the clicker. So, what is the problem with bone fracture healing, and why are we even trying to measure our sensors for them? Well, in order for bones to be healthy, they need to have load on them. That's why we have to work out, be healthy, and just overall keep general health for our bones. However, there's this really important thing that our bones have load for, and that's gravity. Astronauts in space do not have gravity. They experience a lot of microgravity. and therefore their bones don't have load. Without load, their bones loses health and deteriorate, which is a really big problem when it comes to landing. When they land, many astronauts actually hurt their bones and have issues with their bones once they land. So we are trying to develop methods in order to monitor our bone fractures, make sure that we have new methods in order to actually help with these fractures. And in this project in particular, we're just going to be focusing on the implantable sensors. So the objectives for this research is to first implant osseosurface sensors onto the bones of sheep. These sheep are male sheep, and this was going to be a 3-year study. We measure and collect the strain and load of the sheep placed on their femurs, and we analyze the strain over a certain period of time to see how their bones are healing. So first, we need to set up the wireless telemetry system. This is the system that allows us to collect the data. After that, we measure the strain data from the sensors while walking on a treadmill. And then we have to measure the strain data and load data again while the sheep rocks back and forth in order to see how much load they're placing on their leg. And then finally, we use the strain and load data to measure stress. Stress is how much the bone bends physically, and it is the clear measurement of how the bone is healing. So let's start off with the wireless telemetry setup. So on the right over there, that is our sensor, and the sensor kind of works like inductance. So there is a magnetic field that we first induce into the sensor, and that causes current around the sensor. So that's how we're going to power our sensors using magnetic resonance. Then we're going to collect the data using NFC, like antennas. So NFC is kind of like RFID for your credit cards, and that's going to be able to communicate between the wand and the sensor in order to continually collect data from the sensors. On the bottom there, that is the whole system in its entirety. I don't really know exactly what that is because I'm a chemical engineer, but the electrical engineer in our team is the one that designed this system. Okay, so to the walking of the sheep, we walk the sheep for 1 to 2 minutes, and we set the speed to be constant for every sheep so that we have the data to be the same. We measure the strain data on the bone, and as you can see on the bottom, that is an example of the strain versus time that we collect. And then what we do is we measure the peak to peak of that strain data in order to record how much that max strain was, and that's what we collect every day for a certain period of time. As you can see on the right, that's a little video of us actually walking the sheep, and just so that you guys can see, over there is the wand that we use to actually collect data consistently using that magnetic resonance and the sensors that are implanted. Next is the rocking data. So that is actually me over there doing the rocking, and we rock the sheep back and forth on a force sensor, and we simultaneously collect the strain data and load data, and we then use that data in order to gain the stress of the sheep. And yes, so that's how we collect the strain and load data using the rocking data. And then here are the results of our first sheep, Buckbeak. So over week 5 and week 12, we can see that there is a steady decrease of the strain, which is what we wanted to see. We wanted to see the sheep healing and putting less strain on the bone. However, at week 10, we see that it starts to increase again. And this is a really point of interest for future sheep that we study, because we do not understand why we are seeing an increase in strain after week 10. This can be done due to many factors, which I do not know since I'm not an orthopedic surgeon, but we are going to be focusing on those points as we collect more data. Oh, it did not do. Oh, and then here are the x-rays of the sheep over the weeks. Every week we collect a x-ray in order to see how the sensor is doing, to monitor if there's any calluses, any difference in the bone structure, just to see how the sensor is looking inside the sheep. And then, again, I'm going to reiterate our interpretation of the data. We saw the decrease in the strain for the first, from week 5 to week 10, which is good, bone healing. However, we saw the increase from week 10 to week 12, which is really the problem because we do not understand why that is happening. And as we continue to further test, we're going to try to see this pattern and understand why it is happening. So going back to the impact of this lab, we first were able to see, first we were able to prove that our sensors are working right now, implanting these sensors and seeing how the strain changes over time. And we were able to actually get strain data and stress data clearly. And the goal in the future of this lab is to try to implement more measuring tactics and continue to just get better data of the strain and stress over multiple sheep. And hopefully one day we can actually implant these sensors clinically into humans so that we can measure their strain, stress, as well as other important bone factors in the future. I'd like to acknowledge my PI, Dr. David Margolis, our Space Grant Manager, Michelle Coe, and to all of the Space Grant employees that are here today helping the event. My lab manager, David Gonzalez, and my PhD student who really helped me out, Jerry, thank you so much. And thank you everyone for your time. Do we have any questions?
What sort of choices did you have to make in order to keep things ethical? Like, did you break the sheep's humor, or did you find sheep that happen to have broken humors?
We do work with with a specific group that has all the ethicality involved with it, but to keep it, sadly, yes, we do break the sheep's bone, but they're done as ethically as possible, and we are done under an organization that has to be done, but I'm not going to sugarcoat it. Yes?
So, unlike sheep, people are bipedal. Do you have to make any specific compensations around that, or does everything carry over?
I believe we chose sheep because the gait of the sheep step is most similar to a human, which is why sheep are the animal that we choose instead of rodents or pigs, which are actually easier animals to work with than sheep because sheep have a whole lot of different issues with it. However, there is definitely the factor that sheep are four-legged and we have two legs, so we need to definitely keep that into consideration when we try to move this to human trials in the next 5 years.
So you said this applies to astronauts?
Yes.
So are you going to apply this to a workout, specific workout regimes astronauts need to keep up to
I
bone
think
density? Or
yes, I think the biggest thing that it will be used for astronauts is whenever the astronauts work out or whatever their programming is for their bone health, the scientists back at the mission base is able to take the data from the sensors and then make smart scientific decisions to make sure that their bones are as healthy as possible throughout the missions.
Do you have a control room?
Say that one more time.
Do you have a control room?
A control room? A control group?
Yeah.
I think we do have a control group, and
So I'm the PhD. So our control group is just implanting sensors with no fracture at all.
yes.
So that's just our control. We haven't done any of those.
How does it affect the data?
Huh?
How does that affect the data?
It kind of shows the timing between we implant the sensor and the time it takes for the sensor to attach to the bone. So there's a little bit of a few weeks that it takes for the sensor to do that. With the control group, then we can quantify how long it takes for the sensor to bond, and then go from there with the experimental groups.
Yeah, I joined after the control group, so I'm sorry.
What's the recovery time on the removal of the sensor?
I do not believe the sensors are removed, so they are implanted right then and there. So they do not get removed afterwards.
Which works for sheep, but when we go to astronauts, you're going to have to take them out at some point, right?
Yes, so with these, when there's a fracture, since the sensors are very close to the fracture, there's a big callus that overlaps the sensor, so it's very hard to take it out. With astronauts, if there's no fracture, then we're kind of testing how the bone remodels for longer periods of time when you have a sensor in there. We don't know what happens in those cases. But assuming the sensor works, never stops working, then you can basically have it in there. Even so, with astronauts, when they come back, you want to regain the amount of bone health that you had before leaving, then you can just keep it on and kind of train to get to where you were before you left.
So the surgery wouldn't happen until after the recovery was complete?
Yeah.
Okay, thank you.
Any questions from Northern Arizona University?
Should I wait until 2:50 to start or just go on?
It is up to you, it depends on if you have people.
Are you waiting for someone? If not, go ahead.
You want to turn the mic towards you?
Hey, good afternoon, everybody. My name's Selena Lamborn, and I'm a senior chemistry undergraduate at Northern Arizona University. The research I did this year for the NASA Space Grant is investigating the effect of doping on our spin-coated ITO films for potential use in quantum networking applications. So, for some introduction, transparent conductive oxides are a specific class of semiconductor materials that are known for their ability to absorb very little light in the infrared and visible regions of the electromagnetic spectrum. Indium tin oxide, or ITO, is our focus of this study, and it is a member of this class. We made our indium tin oxide thin films using spin coating deposition, which is an alternate to traditional commercialized thin film deposition techniques, such as chemical vapor deposition and magnetron sputtering, which require large facilities and high levels of technical training for use. Spin coating, it can be done benchtop, which reduces the facilities needed for deposition and requires very little technical expertise for use, which is why we were able to use it as an undergraduate. What we're looking for in this study is the presence of an epsilon near zero region, which I will discuss more in depth later, but why we're looking for it is for second order nonlinear optical properties, specifically frequency switching, which can be seen over on this figure right here, where two photons of energy omega interact with this optically nonlinear medium, and then are re-emitted as a third photon with the energy 2 omega, where the energy is conserved but a different wavelength of light is emitted. Additionally, for our quantum networking applications, ITO has the ability to superconduct when doped to a certain charge carrier concentration. So for our study, we're using sodium, lithium, and potassium ion dopants in order to increase the charge carrier concentration and to potentially tune the presence of the ENZ region. So to make these ITO slides, we added 3 atom percent sodium, lithium, and potassium cations into our standard ITO solution with 0.2 molar indium 3+ and 5 atom percent tin 4+. We deposit these onto a glass substrate, and we spin coated with 200 microliters of solution, and we spun it at 1500 RPM, increased to 2000 RPM, and spun for 60 seconds. We dried them in air at 125 degrees Celsius and then 400 degrees Celsius, and then we repeated these 2 steps 3 more times in order to create a 4-layer film. We then annealed our films in hydrogen and argon at 150 degrees Celsius overnight. Then we characterized our films using UV visible spectroscopy to look at the optical transparency and optical band gap of our thin films, and we also used ellipsometry to look at the refractive index, the permittivity, and the extinction coefficient. And for those of you who are not familiar with ellipsometry, there's an emitter, a sample stage, and a detector, and the ellipsometer involves shining a beam of linearly polarized light into your sample, which then is reflected into the detector, and the change in polarization can reveal optical properties of your film. So for our UV visible data, we found that our 3% sodium film had the highest absorption in the visible region, but the lowest in the UV. Our potassium had the lowest absorption in the visible, but higher in the UV than the sodium. And the lithium had higher absorption than potassium in the visible, but that's a typo, higher than sodium in the UV. So then we used our UV visible data in order to generate tau plots, which can show us the optical band gap of our material, which is the lowest energy photon that can be absorbed to begin the excitation of electrons. For our purposes, we're defining a smaller optical band gap as a lower optical transparency as these photons begin to approach the visible region. The band gap energies that we determined fall within our 3 to 4 electron volt range that we were looking for, but the sodium had the highest optical band gap. Additionally, it had a feature around 2.5 electron volts that was not seen for the other plots, but is consistent with this feature seen on the UV-Vis data. And then for ellipsometry, first, the refractive index N is represented by this blue line here. We see that there is a change as the wavelength increases, which is what we're looking for. It shows a strong response to incoming light of different wavelengths. And then the extinction coefficient, K, is represented by this red line. And we see on the right y-axis, the range goes from 0.00 to 0.08, which indicates a highly transparent film, which is also ideal for our applications. And then we use these N and K plots to generate a permittivity plot, where here's the real and imaginary coefficients of the permittivity, epsilon and epsilon prime, respectively. They have an intersection at about 1400 nanometers, which resembles an ENZ region, which is where these two components of the permittivity intersect at or around values of 0. However, we did not see an ENZ region in our films as this intersection happens at 2.5 instead of at 0. So for the future, we need to continue to tune our dopant type and concentrations in order to move this red box down to here in order to see an ENZ region. So to conclude, we found that our films were very transparent in the visible and IR regions, and that there was a change in the refractive index. And while we did not observe this ENZ region at our desired wavelength, we are making progress since our past studies. And in order to hopefully see one in the future, we'll continue to tune dopant types and levels. And we will, as future work, we will examine the electrical properties of our doped ITO thin films, including Fermi levels using XPS and UPS. And here is a picture of a quantum computer, which hopefully we will be able to use our films in. And before I wrap up, I'd like to acknowledge my funding sources and my lab partners, Madison King and Henry Garland, and also my PI, Dr. Stephanie Hurst. Thank you.
Thanks for the readable fonts, by the way. Anyway, so this is the second presentation and where cryogenic temperature are mentioned. So if ultimately one of the goals is to operate this quantum computer at cryogenic temperature, how do you think some of your measurement would change at cryogenic temperature? The results, I mean, which changes do you expect? Do you expect any changes?
There would be changes to the conductive properties, but I can't say that I know for sure what would happen to the optical properties. I would assume that they stay the same at cryogenic temperatures, though. Yes?
I have a question about the dual cylinder. How much surface area can you look at with it? Is it just like a point or?
It's a singular point. Yes.
So per each sodium, potassium, and lithium dope substrates that you did you make multiple of each sample, or was it?
Yes, the slides were made in sets of 3, and the data that I showed were averages of the 3 triplicate slides.
Okay.
Thank you.
So here from Brett Mager and Dr. Trainer from the Real Aeronautics.
Which way is forward? Right. There we go. Cool. Here, I'll go. Do you want to go?
You should stand on the same side, probably.
Okay, cool. Good afternoon, everyone. My name is Zachary Trainer, and I'm from Embry-Riddle Aeronautical University, and I'm a part of the Computer, Electrical, and Software Engineering Department.
And my name's Breck Marr. I'm a member of the Department of Physics and Astronomy, also at Embry-Riddle. And before we start, a very special thank you to our mentor, Dr. John Pavlina, and also Parker Landon over at Boston University. And another special thank you to Embry-Riddle's URI and Space Grant for making this all possible.
And with that being said, our research is on bathymetric LiDAR, the investigation of optimal visible light for non-ideal aquatic environments. So a little bit of background on bathymetric LiDAR, or light detection and ranging. This is a remote sensing technology that depends on the transmission and reception of lasers. And so how this works is it emits a pulse of laser light, green light specifically. And we're using this green light as it has nice effects in penetrating the water. So with this said, we emit a pulse of green light, it penetrates the water, travels down, hits the bottom of the floor of whatever water surface that we're looking at, and then reflects back up and gets sensed. In this case, a big issue with bathymetric LiDAR is the turbidity of that water, specifically suspended particles. These suspended particles can result from many different things, including just natural currents in the water, or someone throwing a rock and particles start suspending. And this can be in the form of as basic as dirt and sand, or even more complex with living organisms. So in this case, our big motivations is to enhance the accuracy and reliability of LiDAR and also contribute to better technology and security and defense applications, as this is used in navigation, in harbor security, and so on. But also, we are hoping that maybe this technology can be used as a new means of space exploration. There are several moons and planets that have subsurface oceans, whether it's been proven or theorized. In this case, we're specifically looking at Europa, and you might be wondering, why Europa? There's so much information, at least in recent times, on Europa, including chemical composition, just a little bit of everything. And in this case, it helps us kind of be able to go into detail that we want to go into for our project. For the objectives, we want to investigate the relationship between these suspended particles and its effects on visible laser attenuation, and then also identify the optimal visible light for space-related bathymetric LiDAR applications, specifically in Europa. So a little bit more background before we can hop into the experiment. The subsurface liquid of Europa mirrors the surface ice in the Earth's chemical composition, or at least it's speculated to be like that. Specifically for Earth's aqueous solution, it's primarily 35%, meaning 35 grams of salts to about 1 liter of water. So in this case, we high-level define salts as NaCl or sodium chloride. And then in this case, we have Earth's ocean, and then Jupiter, Europa is a moon of Jupiter, has a pretty intense magnetic field. And it's also speculated that this intense magnetic field creates MgSO4, or magnesium sulfate. And in this case, as you can see in figure 2, Europa's surface is pretty cracked up and it has a lot of ridges and holes. And so it's speculated that there's a lot of the under subsurface ocean in certain points on that moon meeting with that cracked region, allowing for that magnesium sulfate to kind of leak into the water below. And last but not least, it's also been speculated by NASA that there's hydrothermal activity, which would result in the suspension of particles underneath the subsurface ocean. So with that being said, Europa has a lot of iron, or Fe, on the planet, as its core is made of iron, and so on. And so we are speculating that this hydrothermal activity is kicking up these iron particles. And so in this case, our base for the water that we're testing is NaCl and MgSO4, and then we incrementally add iron.
All right, so let's talk about what we actually did. It's pretty straightforward. We started with a laser. We shot that laser through a foot-long acrylic tube, and then we picked up the light at the end with a photodiode. So let's talk about our tube. The tube is pretty cool. I'm pretty proud of it. It's a foot-long acrylic tube. We'll talk about why it's a foot long in a minute. And then I glued round glass slides to the end with waterproof sealant and cut some holes in the top so we could dump the water out and add some more in. It was really awesome. But in that tube, we'd hold our water solution that we'd shoot our laser through. And I also made note of the laser wavelengths we used here. So we used a red 650 nanometer laser, a green 532 nanometer laser, and a blue 405 nanometer laser. We chose these three because they're really easy to find, you know, like laser pointers in red, green, and blue. That's exactly what these are. All right, so to take data, we first needed to find a baseline so we could have some sort of intensity comparison, right? So we shot the laser straight through air to our photodiode and measured the intensity. And then we shot our laser through the tube, empty, through the tube with distilled water and nothing else, and then through the tube while it was wet, because why not, right? And so to take trials from there, we first started with the tube full of our magnesium sulfate and sodium chloride solution, so like our base salt water, and we'd incrementally add iron and take intensity measurements along the way. So for each addition of iron, we'd take 3 measurements, 1 for each wavelength of light. Oh yeah, so the laser's a foot long, and that was very intentional because you need about a foot of water to really see any noticeable effects on the intensity of your beam traveling through your solution. And as you can see here toward the left, there's not as much going on as toward the right, which is what we'd expect. All right, so for our results, we plotted everything in comparison to the initial intensity we got shooting through just distilled water. So on the left is that intensity, that's our y-axis, and then our x-axis is the amount of iron in grams that we added. And as you can see here, our blue light actually did the best consistently. And then in the middle we've got red, and on the bottom we've got green, and they're being outperformed by blue consistently. And this pretty much lines up with what we'd expect based off of an iron absorption spectrum. It absorbs really well in the green and the red, and not so much in the farther blue. So we didn't break the spectra, that was good.
There we go. And now looking forward, we have 2 main conclusions. One being that the water mixture likely influenced the scattering and absorption of that green light, which is traditionally used in bathymetric LiDAR. And again, as Breck had previously said, this is expected just primarily due to the iron. And then also, we never had the opportunity to look at the magnesium sulfate, and so that's one of our future plans to do in the future. And then also, assuming there is no organic material, which it's been speculated there is, but we really don't know, blue light might be preferable. And that's another future step, is what if there is that organic material? Will it behave the same, and will blue still be the best?
Yeah, and so looking forward, this is pretty preliminary, pretty baseline stuff that we've been up to so far, but there is a whole lot of room for expansion because the ocean is complicated. So there are so many other particles we could try, and we could also maybe mess with a current, see how that might affect our results with different particulates in the water. And as our solutions get more complicated, maybe taking spectra to kind of anticipate what results we'd be getting. But that's it. Thank you so much.
Question?
So the first is a quick comment. Behind the dam of Willow Lake in Prescott, people know there is a train motor that is hidden there. They don't know where it is. Definitely is muddy, particulate water. So if you have a way to find it, we have a project for next year. The second question is, on Europa, the ocean is expected to be ballpark 50 to 100 kilometers. So how much power you're going to need to go through, and whether you put your sensor on the other side of the moon. So it's a little bit of a challenge. And the third thing, if you are interested, I publish a couple of papers on estimating the ocean on Europa, so we can talk after. So, but do you have comments about the second question about 100 kilometers? How do you?
Oh yes, it would take a lot of power, especially if you're expecting to reflect that all the way up. I know that they use LiDAR to map like the optic cables that they string under the ocean, but that's not quite so far. So it would take a lot of power and some creative engineering, that's for sure.
Questions in the back?
What advantage does LiDAR have over other sensing methods in water, like radio waves or sonar, for that matter?
It's a great question. Off the top of my head, I don't directly have an answer. Specifically, we just primarily chose LiDAR just due to our personal interests. This was kind of just a little fun thing we wanted to do on the side.
You can measure the thickness of the ocean using spontaneous meteorites that impact on the surface of the ice, and then you look at the delay of the internal reflections, and by looking at the structure of the reflection, you can measure that. But NASA has decided to invest in the next Galileo mission mostly in the magnetometer, because the salty moon behaves like a dipole, an induced dipole, and they think it's easier to detect variability in the magnetic dipole from the presence of Jupiter. So currently NASA is investing on the magnetometer.
Another question in the back?
Does the glass at all impact the laser?
It will, yes. I mean, Snell's law and such, but of course it's a ratio, so it will impact it equally.
Okay, cool.
Yeah, you mentioned about the green light sonaring and the one. Are you studying any other light color spectrum for getting the maximum output?
In what regard? Like with just traditional bathymetric LiDAR, or?
Yeah.
For traditional bathymetric LiDAR, there have been studies done, and essentially they use green just because it doesn't scatter as much. But primarily it has a nice balance between actually penetrating the water. For example, red has a hard time penetrating the water compared to green and blue, which do not. But blue likes to really go crazy underneath the water, depending on the wavelength within that blue spectrum. Yeah.
Thank you.
Okay, well, I'll try. Yeah, okay. Hello everyone, my name is Serena Blanchard. I am a junior studying mechanical engineering here at the University of Arizona, working on a project called WINDS, which is the Waves, Instabilities, and Noise Spectrometer for Earth's ionosphere, under the guidance of my mentor, Naomi S. Starting off with our project goals, we aim to develop an instrument capable of flying on a CubeSat that could take electric field measurements of the ionosphere up to very high frequencies. For our instrument, we want to measure plasma parameters and waves to the same accuracy as existing solar wind payloads while maintaining a smaller size and lower cost. For this project, my specific focus was to develop an analog to digital, or ADC, printed circuit board, or PCB, to convert the input signals, which are analog, into digital signals that we can analyze. So starting off with, what is the ionosphere? So while the exact bounds of the ionosphere are not defined, it's generally considered to be between tens and hundreds of kilometers above the Earth's surface. What's important about the ionosphere is that it's ionized by solar radiation, meaning there's large amounts of charged particles. Some of the phenomena that we aim to understand that are either influenced by the ionosphere or can influence the ionosphere are auroras, tides, and plasma fountains. Plasma fountains are outbursts of plasma near the polar regions of Earth that appear fountain-like. So while our main focus of this project is to develop an instrument, it's important to consider the conditions it'll face once it's in space. The most important is getting enough power. So our instrument's going to fly on a CubeSat that's going to be covered in solar panels. However, our CubeSat is going to be spinning around rapidly, which means it's going to get inconsistent sun exposure. Because of this, we may get power fluctuations, just having inconsistent solar power on our solar panels. Along with that, it's going to cause temperature variations. So the side of the CubeSat that's facing the sun is going to get really hot the side that's facing away from the sun is going to get really, really cold. And so we have to design all of our instruments and choose our hardware to be able to withstand those changes in temperature. There's also noise in the ionosphere, so we're going to have to filter that out either through code or physically using hardware. And then on the mechanical side, we have to fit everything within a 1U CubeSat, and so everything must fit within a 10 by 10 by 10 centimeter cube. So this is the concept of operations for our PCB. Data gets picked up by our antennas, and then that gets sent to a glitch filter. Our glitch filter filters out any noise that we may have. And then once the noise is filtered out, those analog signals get sent to our ADC. This is where the actual conversion takes place. So our analog signals get turned into digital signals. Once we have our digital signals, those get sent to our connectors and then to our FPGA. Our FPGA essentially acts as a mini computer, so it'll process our data as well as supply power to the rest of our board. If any of you saw Maud's talk, he also spoke about some of the processing that we're going to do. So our FPGA supplies 3.3 volts. That gets sent to a voltage regulator, which bumps it down to 1.8 volts, and that gets sent to our ADC to power it. This is how our actual PCB turned out, so it's pretty similar to our first concept of operations. We did have to add an IC transceiver as well as another voltage regulator. So our second voltage regulator actually does the same thing as our first. It takes 3.3 volts from our FPGA, drops it down to 1.8 volts, and feeds it into our ADC. However, one of our voltage regulators is for an analog voltage, the other is for a digital voltage. Our IC transceiver acts as a low voltage differential signaling driver, which basically means it takes a higher voltage from our FPGA, so for example 3 volts, and it actually splits it into two lower voltage signals that are opposite signs. That gets fed into our ADC, and then our ADC outputs those same signals. Our IC transceiver splices them back together into one higher signal, and that gets sent back to our FPGA. These are some pictures showing the different designs that we went through for our PCB. The one on the left is our very first design. The one on the right was our most recent design. You can see as we worked on it, we discovered that we needed to add more things, for example, an IC transceiver. We also decided that we needed to reorganize the board to make it more symmetric, which can help reduce noise. You may also notice that the two on the right are kind of funky shapes, and we'll talk about that in a second. This is how our actual PCB turned out. Everything was hand soldered by me and my mentor. Most of it's surface mount except for our connectors, which are through hole. We got it printed from Osh Park, if anyone is wondering why it's purple. So let's talk about why it's this crazy shape. So it's actually because of our glitch filter. If our glitch filter is in line with our ADC, it can cause noise and interference. And so we had to rotate everything except for, this is our ADC right here, this is our IC, and we have some connectors. So we rotated everything to be 45 degrees in order to avoid the unintentional interference. So we didn't get the chance to do extensive testing on our PCB yet, but we were able to do some initial testing. The graph on the left shows that our PCB will accept an input signal and will also output a signal, which is great news. It means that it should work. Nothing is shorted in it. The graph on the right is what it looks like when we transmit data over our D0, which is our data output pin. We don't have the code to process this yet, but it does show great promise for the functionality of our PCB. The little spike you see right in the center, that's from our clock signal, which is also a good sign. And this is another graph that we got from our testing. So the bottom is a clock signal, the top is our data output signal. So we fed in this clock signal, and then this is the output that we got. This one's actually a little bit unusual. It took us a bit to figure out why it looks this way. If anyone has worked with SerDes before, this is a bottom clock signal. And so every time that this clock signal is at a maximum is when our top signal should send data back. But if you look at it, we're getting data from our top signal a lot faster than our bottom clock signal. So doing a little bit of research, we figured out that it's because our ADC multiplies our clock signal by 20 in order to transmit data faster, which is pretty cool. All right, so the Space Grant Symposium kind of marks the end of the Space Grant internships. However, there is still more that needs to be done. The most important, and just the next step in general, is to do more intensive testing and data decoding especially, so we can analyze some of the graphs that we're getting. Along with that, we need to implement changes we discovered during testing. So before we started testing, we already knew we needed to switch out our voltage regulator to one that's easier to solder. And we also changed the design to include standoffs, which is shown over here, which will just make it easier to handle. I've also been working on another version of this PCB that has a different model of ADC in it. During our initial testing, we discovered that our PCB draws a lot more power than we anticipated and can realistically supply. And so we're working on looking at different models that have better power consumption. Yep, and then we also need to figure out a mounting system within the CubeSat whenever it's ready to be flown, and also how to integrate it with the rest of our instrument. So thank you to my mentor, Naomi Eskis, my PI, Mihailo Martinovic, and my fellow space grant intern, Ahmad, as well as my shulko and my dad, who helped me every time I got stuck. Thank you.
First of all, kudos for soldering that QFPN package by hand. That's impressive. Highly would recommend getting a stencil for assembly. It really makes things so much easier. I think my one question was, while it's significantly below the ionosphere, have you considered flying this experiment as part of the Ascend project?
I don't think we have. This is kind of a separate, higher level project, and so we definitely have the option. I am also the Ascend team lead for U of A, so we do have the option to do it. But maybe if we get a full prototype and we can kind of risk it being destroyed. But Ascend flights are pretty risky, so I don't know if we want to risk that.
Yeah, sure. This is like way out of my realm. Could you go into a little bit of how the orientation of that part affects the noise?
I'm not super certain. It was something that was said in the ADC manual, and I just kind of went with it. Naomi, do you happen to know? I think just like when it's in line, it's pretty sensitive. Like the ADC is just as sensitive, and because it's an analog signal, maybe there's more interference as well. It didn't actually want anything to be in line, and we looked at a couple different iterations that had that same chip in it, like prototypes that already existed, and they also had it be 45 degrees. So for some reason, it's very temperamental.
Assuming you have different grounds for your domains, do you have a way to deal with a potential difference that could develop across the grounds?
We do. So I don't know if you guys saw on the last design, but we actually have an analog ground for the front half and then a digital ground for the second half. And so between those, we have Schottky diodes to help minimize voltages being transferred between the two.
So is there any reason you chose to rotate a lot of components on the board rather than just say, okay, take my ADC and 45 degrees?
The main issue was routing. I don't know if you saw the ADC. It has 48 pins, and it's about 1 centimeter by 1 centimeter. So it's pretty hard routing. It was easier to have that be straight up and down and then rotate everything else because it was pretty simple. We definitely could do that for the next iterations, though.
Following along that question, do you see mounting that into the CubeSat difficult with the rotation?
I don't believe so. The way that the PCB is built, like there's not going to be any noise. There shouldn't be any noise if it's in line with anything else. And so we should just be able to layer it with the other components or like layer it on top of the FPGA without too much hassle. But we can always see when we assemble it.
Okay, let's thank the speaker again.
Next we hear from Grace Morris.
Okay. So I worked on the development of machine learning assisted surrogate models for complex space structures. So the motivation behind this project is that complex space structures have lots of components, which makes them complex and difficult to analyze and have very complicated behavior. And then when you add material uncertainty on top of that, it makes it even more complicated. So using surrogate models and machine learning, you can simplify and increase the computational efficiency, basically. So this is really important because you need to know like the deformation of these space structures. Like you don't want to overload a space structure because it's very expensive to build them. And also you need to know where all your components are at if you're going to be docking and undocking. So using a surrogate model, you can do that analysis much more efficiently. So the main objectives are to develop a finite element analysis model of components of the International Space Station using available specifications, and then to generate the training data set to actually generate those machine learning assisted surrogate models. So the first thing I did was create the physical model. So I use SolidWorks primarily, and then there's a Blender file available of the International Space Station. You can see circled in red the original like actual space station components that I modeled. And then
on the other side, there is my actual model in SolidWorks. I have some 3D printed components to kind of give you an idea of like the size and the shape of what it looks like. So this is the actual truss module that you see in the center, and then the solar panels for scale, kind of. So once I had the physical model completed, I had to move on to material assignments. So like I said, there's material uncertainty and everything. So for all the metal components, I used aluminum 2219 because this seems to be the most common metal used in space structures. And then for the solar panels, I modeled them as gallium arsenide because that's the primary component in space solar panels because it's got a higher efficiency. In reality, solar panels are lots and lots of layers of different metals and electronics and everything, but I modeled it all as gallium arsenide for simplicity, basically. So once that was done, I was able to move on to the actual finite element analysis. I used ANSYS Workbench and ANSYS Mechanical together to get this done. So here you can see a snippet of my ANSYS Workbench with square A having kind of all the setup of the problem, and then these other sections basically have the different loading conditions, so that makes it really easy to add different loads and different perturbations of materials. So this is an example of a static loading condition. So this has a downward force applied here on one side of the solar panels, and you can see the deformation kind of decrease as you look through the system. For a sense of scale, the deformation here is less than a millimeter. It's about 0.1 millimeters at the max deformation. But this is a static model, and I did several other static models with loading on both sides, pressure loadings, different kinds of basically static loading. The next step was to move on to natural frequencies and mode shapes. So this is all really important for dynamic analysis. There's going to be lots of vibrations that you're dealing with when you're docking and undocking various spaceships from the International Space Station. So I checked the mesh convergence, and as this graph's also helpful because you can see this is where we end up operating. So just over 100,000 elements were used for the analysis. And then this graph here is our first natural frequency. You can see the max deformation is on both sides for that frequency. This has a slightly higher max deformation of about 1 millimeter. So it makes a big difference when you have natural frequencies. It's roughly an order of magnitude higher for a natural frequency deformation versus just a static loading condition. So the mesh convergence check, it looks like that, like it appears as though there's huge differences, but the difference is really less than 2% for the deformation and less than 1% when you look at it on a frequency basis. So I just wanted to point that out. It looks like it's a steep slope, but it's really not. It's just because of the scale. And then once I have the models all generated, I'm able to move on to the material uncertainties and different perturbations. So these are the different material properties that we were looking at. So Young's modulus, Poisson's ratio, your shear bulk modulus. So all those are very important basically for deformation. The different perturbations were generated using a log normal distribution. This distribution was used to ensure that our values don't go negative. So basically just keeps them where they realistically should be. And then the mean values were pulled directly from ANSYS. ANSYS has a whole list of all the material properties at the different temperatures. So conclusions, ongoing work. Using this data set to be able to create machine learning assisted surrogate models is really important, and it alleviates computational burdens for any future work of complex space stations or complex space structures. Ideally, I'd like to expand the model to include more of the International Space Station, because as you saw, it's just a portion of it. But with the ANSYS background already set up, it would be relatively simple to just upload a new geometry file. And then the next real step is to actually take the training set that I'm making and use the neural network and variential autoencoder to actually generate the surrogate models. Both of these tools have inherent capabilities to represent the material uncertainties, so that makes them really great for this application. Any questions?
combination of natural frequency and static reaction? Is there a way to instantaneously put those together?
I think you can do it as like a chain of events. So you could do the like static and then chain those results as an input into a natural frequency or vice versa. But I don't think you can do them simultaneously.
I have another question. Your analysis does include the possibility of oscillation that are non-linear. For example, if there is a collision with a small object that excites vibration larger than the linear regime.
Yeah, I want to be able to do that, but it doesn't account for that right now.
So how do you offset the deformation?
What? Oh, the force in that example was 5 newtons, I believe, but there are other ones with, like, I ran several different perturbations for forces and different loading conditions, so I don't think I went higher than 25 newtons, though, in any of them. Yeah.
Yeah, second, Arizona State University.
Hi, my name is Saket Shandog, and my project is FPGA-based radar signal processing. I'd like to thank my mentor, Tracy Jameson Hooks, for helping me with this project. I know this sounds like a lot of electrical engineering jargon, so I'm just going to break it down for you very quickly. An FPGA is a field programmable gate array, and is basically a reprogrammable circuit board that runs on digital logic. And and it allows for a high data rate because they are massively parallel structures compared to like a microcontroller, which is sequential. So this allows us to transmit data very quickly, and it also allows for rapid implementation and testing due to the reprogrammability of them, as they are constantly reprogrammable compared to like a pre-made chip or an ASIC, which is make it once and remake it again if it breaks. For this project, we'll be utilizing a millimeter wave radar to measure the 3D mass distribution of ash clouds and plumes. Millimeter wave is ideal for this scenario as it's better matched for the ash cloud size. Millimeter wave is between 30 to 300 gigahertz, and the wavelength is between 1 centimeter and 1 millimeter. And this allows for better sensitivity for the sensor to allow for less noise and better data accuracy. This is useful for on-site testing of the ash particle, as we're trying to create an instrument that will analyze this on-site very quickly, as it can cause flights to be grounded across continents, which is a significant issue in the airline industry. Could you press that? Oh, wait. Oh, it's upside down. That was my issue. Okay. Okay, so this is a basic block diagram of what I am making. It starts off with a chirp transmit signal, which is frequency modulated through a digital analog converter. Frequency modulation is basically changing the frequency to transmit data, as the changed frequency represents a different bit length. And then that is bounced off of the ash particles through the RF analog front end, which goes to an analog to digital converter, which is then mixed with the original chirp signal to then create a low and high frequency signal. And then that data is gone through a fast Fourier transform and then a spectral averager, which is shown by that mag and average block. And then it is going through Ethernet data output to a base station. This is, again, shown here. This says polyphase filter bank, which is what we changed to later, but all of my diagrams and data is using a fast Fourier transform, but all of the data will be using the FFT compared to the polyphase filter bank, because that will be done in the future. So the first step is to do a simulation in MATLAB. We use an NCO, which is essentially a numerically controlled oscillator, which is a sine wave that we will be pushing through the digital backend, which is what I'm designing. And the point of this is to see if the algorithm will work correctly before we actually put it on hardware, because we don't want to waste a lot of time doing it because hardware is very complicated and messy. So this is the expected output. We just use a 25 megahertz signal as the NCO frequency, and it is shown properly through the MATLAB output. And then the hard part, hardware testing. I had a lot of issue with this because FPGAs are very new to me and they are very annoying and complicated. I understand the basics of digital logic, but there's a lot of nuances behind timing and port constraints that I was having a lot of issue with. But eventually I deliberated and got through it. And the Simulink design is then coded in the hardware description language, which I use VHDL in Xilinx Vivado to program the FPGA to run this algorithm. And then I utilize the internal logic analyzer in Vivado, as we will not be outputting this to anything yet, so you'll just want to see what the data looks like on the FPGA itself. This allows for functional verification of the HDL code when it is performed. And the signals analyzed should demonstrate that the digital spectrometer works. And then this is the repeating time signal on the FPGA that we're using, showing that the output did work properly. The next steps are essentially I have to wait a lot because the RF front end needs to be designed and I do a lot of testing with that RF front end. But once that is designed, I can do testing and modify the algorithm. And then the chirp signal and frequency mixing also needs to be designed, which again will be done after the fact. Right now, I'm working on the Ethernet data output and transmitting that as quickly and as low loss as possible. And I would like to thank Dr. Tracy Jameson Hooks, my advisor, Arizona State University, and the NASA Space Grant Program. Any questions?
What type of data are you expecting or hoping to get?
I'm honestly not quite sure. The volcanologist on the program has said a lot of things that I just do not understand. I'm essentially just designing the digital back end of it, but I might ask and get back to you.
Oh, wasn't clock configurable on that?
What'd you say?
Wasn't clock configurable on that?
I completely forgot. I think it was, we did the digital testing at 20 megahertz, but I think we'll be able to do quicker than that.
Something that is more like a praise of this kind of conference. I don't know if you know that, but there was another presentation early this morning of someone trying to do something similar to monitor ice crystals into clouds.
Mm-hmm.
And maybe the two of you can talk to each other.
That'd be interesting. Yeah, I'll definitely look into that. Any more questions? All right. Thank you very much.
Thank you so much for coming to our talks and presentations today. I've been encouraged to ask you to take your name badge and turn it back into the front table, as well as fill out a short response survey in exchange for an award. I have not been told what the award is. Go find out.